Okay, so today we're going to be looking at chapter 13 for the first time. We're going to look in 13.1. I'm going to pull up the note screen and we're going to talk about what 13 is all about. So, sharing my screen now. Okay, so you should see my note paper. You guys, in chapter 13, we're going to be talking about antiderivatives. So we know what a derivative is, and the word antiderivative implies the opposite of that, right? Which is exactly what we're doing. You guys, we're going to be going backwards. So we have to, we've just got to change, our habits, because when you see, for example, hold on. So when you see, for example, a function, maybe y equals 3x squared, at this point, because we've been doing derivatives so long, it really makes you want to take the derivative, right? And then you get the 6x, and that's satisfying because we're using the power rule, and we do that all the time. But you guys, we're going to go the other direction now. So this is a true statement, obviously. If your y equals 3x squared, then the derivative of y equals 6x, because that's how it works, guys. But what if today I gave you a function y equals 6x, and what I'm going to ask for is for you to find the antiderivative. So when you see the word antiderivative, what I want you to think about is think of the function I'm giving you as a derivative. Say, okay, 6x was the derivative of something. I want to know where it came from. So you guys, again, we're going backwards. We're starting with the end product. We're starting with the derivative, and we're going to go backwards. You guys, so the antiderivative, well, you'd say, okay, if 6x is the derivative, then, just by logic and thinking, and because I have this written up here, you say, well, your original function had to be 3x squared. Or that's one possibility. So you guys, this is what we're thinking about, going this direction. Antiderivative is going from a function that I am assuming is the derivative of something else, and I'm going back and I'm finding that original function. So you guys, one thing that we want to note is notation. So you guys, instead of just writing out find the antiderivative every time, I will be, so you'll have a function. Let's say your function is 6x, and I'm writing some things around it to help you out. I'm going to help you out on what they mean. You guys, so notice I've got kind of a squiggly, it's kind of a long, like if you took an S and you stretched it top and bottom. You guys, that's what I would say. You guys, so we have this symbol here, and it's a symbol for finding the antiderivative. Another word we use when we talk about finding antiderivatives is integrate. I might say I want you to integrate this function. And I want you to notice there's a dx here. You guys, this is going to be the notation that says I want to take the antiderivative of 6x with respect to x. So we know that dx usually means with respect to x, and that's what it means here, but notice it's not written as a fraction. And you guys, we are going to need it there because at some point we're actually going to do something with this. So remember how when we were doing derivatives, we had like dy dx, and for a while it was just notation, wasn't it? Until we started doing implicit and we had to use it a lot. So that's what this is going to be like, guys. For a while, it's just notation. It just says what we're taking the antiderivative with respect to. But we do need it there because at a point we will need to use it. So the antiderivative of 6x dx, well, remember I already found that. I said, okay, so if 6x is like the derivative, I'm going backwards. And the original function would have been 3x squared. But there's actually going to be another term here, and I'm going to show you how to find that. So let's go back to what we had over here. I said that in this very first example, if your original function y is 3x squared, then you take the derivative and you get 6x. That is absolutely true. But what if our original function was, and we'll go back up to what I have there. You guys, what if my original function was y equals 3x squared plus 5? When I take the derivative of 3x squared plus 5, I still just get 6x, right? So if I started with the 6x and I said this is like the derivative, what was the original function? Could I have said the original function was 3x squared plus 5? And that still be a valid answer? Absolutely, because the 3x squared is the important part, right? I can add whatever constant I want on my original function because it's going to go away when I take the derivative. So when I see this 6x, I'm like, okay, I know it definitely came from 3x squared, but there's no way for me to know if there was a constant there or not. What if I had started with 3x squared minus 7? What's the derivative of that? Oh, it's still 6x. So if I was taking the antiderivative and going backwards, could that be a possible answer? So I got a derivative of 6x. Could it have come from 3x squared minus 7? Yeah, because adding and subtracting a constant on the end doesn't change your derivative. So you guys, let's go back up. And notice that when we take an antiderivative, we actually have a lot of options. Now, this 3x squared is definitely going to be in my answer because that's how you get the 6x. But there's no way for me to know if there was a constant with the 3x squared or not, because you know when you take the derivative, it goes away. So we allow for that by writing plus c on every one of your antiderivatives. And what this plus c is just any constant. It takes care of that. So when I read that my answer is 3x squared plus c, what it's saying is, okay, my original function was 3x squared, possibly with a constant at the end. I don't know what it is, but I'm going to write plus c to note there could have been a constant there. And you guys, this is actually going to be very important because we do need to know that a constant could have been there. So you're going to get really used to writing plus c for these antiderivatives. There will be a time where we get a little bit more specific. And so, for example, we'll actually solve for a constant that was there in some applications. But in just a general form, you guys, you take an antiderivative, there could always be a constant on there, so we put that plus c. So you guys, here's the thing. When you're going backwards, you know, it isn't always just you thinking, okay, so let me think about what this came from, because sometimes these functions can be really complicated. Like with the 6x, it was pretty easy to go backwards. But you guys, we actually have rules. So we don't have to sit and think, okay, where did this function come from? And, you know, you guys, we have a set of rules for taking antiderivatives. And the first one is going to be the power rule. So this way you can look at a function, even if it's really complicated, and find the original. So we can integrate even complicated functions without having to just sit there and think about it like we did on this first example. So this is going to be the power rule. for antiderivatives. So remember, you have a power rule for derivatives. Now I want a rule for the antiderivative. So I'm going to write it down for you. So you guys, let's say you have, let's say we have a function. Let's use function notation just to switch it up. You guys, so the function given is going to be f of x equals x to the n. So you have x raised to some power. That's your original function you're given. And I want to not take the derivative because I know how to do that, right? If I wanted to take the derivative, I'd put the power in front, I'd take one away. That's what we're used to, but we have to go the other direction. So everything we did in the power rule for derivatives is backwards. And I'm going to write down what we do here. So if I take the antiderivative of this function f of x with respect to x, notice that that would be the antiderivative of x to the n with respect to x. What I get out, you guys, is it kind of looks similar to the power rule, but it's a little bit different. You guys, you're going to always get out 1 over n plus 1 times x to the n plus 1. So before we do an example of this, I want to make sure that this makes sense on why we're doing it this way. Let's recall the derivative power rule. If you had a function f of x equals x to the n, and then you took the derivative, what did we do? Well, we just brought the n in the front and took one away. Can you see, since we are going backwards, why in the derivative function we were taking one away, but this time we're adding one? And notice in this function, we're multiplying by a number in the front, but this time we're dividing by a number in the front. So you guys, it is absolutely the opposite of the derivative power rule. And it is hard to get used to because it's the opposite. But let's do some examples and utilize it and try to get us used to it. So you guys, let's say I have y equals x to the 7th. And I want to find the antiderivative. So you guys, the antiderivative of x to the 7th, remember the dx means with respect to x, equals. Let's use the power rule for antiderivatives. So you guys, your n is going to be 7. It says I do 1 over n plus 1. So 1 over 8. And then I have x to the n plus 1, and I get x to the 8th. So you guys, I have taken the antiderivative of x to the 7th with the power rule, and I got 1/8 x to the 8th, but I'm not going to forget this could have a constant on it, you guys. This general form of antiderivatives are always going to have a plus c because we don't know if there was a constant there or not. So let's do another one. What if I have y equals x to the -4? So you guys, you might wonder, well, what if your power is negative? Does this rule still work? Well, it still worked with derivatives, didn't it? I use the power rule on negative powers all the time. So I think it'll be fine. You guys, so let's say we have x to the -4. And I want to take the antiderivative, or I want to integrate x to the -4 dx. I'm just going to use the rule. I will write it down again. 1 over n plus 1, x to the n plus 1. So you guys notice in this case, your n is -4, so I just need to be careful with the negative. But when I integrate or take the antiderivative, I'm going to get 1 over -4 plus 1. So 1 over -3, and then I'll have x to the -3. And don't forget, plus c. There could be a constant on there. So you guys, it works on all the same exponents. It works on for, taking the derivative. There is one special case we're going to look at. here in a minute, but I'm not ready to look at it yet. What if I have a square root? What if I have y equals the square root of x? And I want to take the antiderivative of the square root of x. Well, you guys remember when I was doing derivatives, I turned the roots into powers so I could use the power rule. I'm going to do that same thing here. So you guys, I'm going to rewrite this as x to the 1/2. And then I'm going to use the rule. You guys, with my n equals 1/2, just side work, you guys, what's n plus 1? Well, 1/2 plus 2/2 is 3/2. So this is the number I'm going to be using when I need n plus 1. So let's write it out. I have 1 over n plus 1. So 1 over 3/2, and I'll simplify that in a minute, x to the 3/2. And then I have a plus c. And you guys, let's rewrite this a little bit. When you take 1 over something, it's the same thing as taking the reciprocal. So when I see 1 over 3/2, you can just flip it over and get 2/3 x to the 3/2 plus c as your answer. So you guys, yeah, so anytime you have 1 over anything, like if you see 1 over x, that could just be 1 over x, but you could also see it as taking the reciprocal of x, because 1 over x is the reciprocal. X over 1 is where you would have started and then you flipped it over. So you guys, anytime you have 1 over something, especially a fraction, you can just flip it. Okay, so you guys, let's put a coefficient on there. We might wonder, well, what happens in a case where you have a coefficient with your x term? Maybe I have 5x to the 4th. Well, you guys, just like in derivatives, coefficients just come along. So you guys, because the coefficients, for example, when you take the derivative, this 5 would just come down the same, right, as a 5. So if you went backwards, it would stay the same because it stayed the same the other direction. So you guys, coefficients just come down. And then we do the power rule on the x term. So you guys, if I want to take the antiderivative of 5x to the 4th dx, what I'm going to do is I'm going to bring the 5 along, and then I'm going to do the power rule on the x to the 4th. So you guys, if n is 4, then 1 over n plus 1 is 1/5, and then x to the n plus 1 is x to the 5th. I do have a plus c. And you guys, what's nice about this one is that you can multiply this coefficient with the 1/5 and they just cancel each other out. And you end up with just x to the 5th. But you guys, as I get these answers, you should be able to confirm them for yourself. You guys, remember, we're treating what they give us like it was a derivative. We're trying to find out where that derivative came from. You can always check these. You guys, what's the derivative of x to the 5th? Well, it's definitely 5x to the 4th. But you guys, this power rule is getting us there, so we don't have to sit and think about it every time. What if I have, let's do x cubed over 4. And I want to take the antiderivative of that. So don't let this one throw you off on the writing. That over 4 is actually a coefficient. Remember, you can pull the x away from the numbers. So that's what I'm going to do first. You guys, just rewrite this. Isn't this the same thing as 1/4 x cubed? You guys, pull them apart if you need to, like in this case. It's just easier that way. So what am I going to do when I take the antiderivative? I'm going to bring the coefficient along. Then I am going to use the power rule where n is 3. So it's 1 over n plus 1. So I get another 1/4. and then I have x to the n plus 1, and I have plus c. So in this case, you guys, I would just multiply these two fractions together and actually get 1 over 16 x to the 4th plus c. But you guys, let's look at this next one. You guys, well, let's talk about that case where the power rule breaks down. I have my y is going to be just 1 over x. And so I want to take the antiderivative of 1 over x dx. Well, you guys, when you have an x in a fraction, like on the bottom, a lot of times we just write them as negative exponents, right? So we can use the power rule. So you guys, that would be a first step. Instead of writing 1 over x, I'm going to write x to the negative 1. Now I say, okay, I'm going to use the power rule where my n is negative 1. Let me rewrite the power rule over here so we have it. Remember, it's 1 over n plus 1 x to the n plus 1. So if negative 1 is our n, let's try to take the antiderivative using this power rule. So you guys, I do 1 over n plus 1. What's negative 1 plus 1? A 0, right? And then I have x to the n plus 1 again. You guys, x to the 0 is not a problem, but this is a problem, guys. So my power rule has broken down. You guys, I can't use it for this case because I get a 0 on the bottom. So on 1 over x, when you have just an x to the first down in the bottom of whatever function you're looking at, we can't use power rule. Now you can try all you want. You can, try to use it, and then you're going to see that it doesn't work, and you're going to have to think about why and what you can do there. But you might just want to remember, if you ever see x to the negative 1, or you have x on the bottom, but it's just x to the first on the bottom, that's going to be a problem when you try to use the power rule. But let's think about 1 over x. Remember, going backwards. You guys, if the derivative of some function is 1 over x, what function did that come from? Why is the power rule breaking down on us here? Well, let's recall. Where have I seen 1 over x before? You guys, if you have a function f of x equals the natural log of x, and you want to take the derivative, what do you get? You get 1 over x, right? So don't you think when you're going backwards, I should end up with natural log as my answer? You guys, this is why the power rule is breaking down here, because it's not actually a power rule problem. This is the natural log problem. So you guys, because we're going backwards, if I want to take the antiderivative of 1 over x, I'm going to get a natural log. Now, I'm going to write it the way it's going to be written, and I'll explain why. You guys, so 1 over x going backwards becomes natural log x when you take the antiderivative. Now, this part with the plus c, that's always there. Why did I put the x in absolute values, though, is a question that you might be wondering, because, really on top of all of this, you're going to just add in some absolute values, to make it worse. Well, guys, the reason why we have to put x in absolute values, let's look over here what we have here. When the original function is natural log x, that's what you were given. And if you are given a natural log x, this assumes, you're assuming that x is positive because it gave you this function, and you're assuming that that function is defined. And if you don't remember anything about natural log or logs in general, this term has to be positive. It cannot ever be negative. So if the book, for example, gives you a function that says, hey, f of x equals natural log x, you can assume x is positive, and for all intents and purposes, that's what they want you to assume. Or if I gave you that problem, again, it's in function notation. It seems like it works. I can assume that. So when it's given like this, you can assume it's positive, so you don't need to make sure it stays positive with absolute values. When I take the derivative, I don't use absolute values because I'm assuming this x is positive. And honestly, when I put it into the 1 over x, who cares if it's positive or not? That function would still work. But you guys, the problem comes when I'm going backwards, because all they're giving me is 1 over x. Because it's not in a log statement, there's no way to assume that x is positive or negative here, because if you just have 1 over x as an expression, x could absolutely be positive, but it could also be negative, and that expression would be fine. So you guys, because I cannot assume that this x is always positive because there's nothing restricting it, because I am introducing the natural log statement, because we are introducing that statement, when we put this x in here, and we don't know if that x could be positive or negative, we put it in absolute values. So if you don't understand exactly why we're putting it in absolute values, when we didn't have to before, that's okay. Basically, if your book gives you a natural log question and doesn't use absolute values, that's fine. We assume that it knows x is positive. But when you introduce the natural log into a problem, you always need the absolute values. So if you just remember that you need them because you're the one introducing the natural log, that should help. So I started with 1 over x. I figured out the power rule broke down, and I figured out that the answer there is actually the natural log of absolute value of x and then plus c. That can look a lot of different ways. You guys, what if I have y equals 3 over x, and I want to take the derivative, or sorry, antiderivative of 3 over x dx? Well, what do you think about that 3? That's just a coefficient, right? Just like I did when I had the fraction with the x and I took the number away from the x, you can do that here. You guys, this is the same thing as 3 times 1 over x, isn't it? So you guys, if you've got just a number up here other than 1, you can take that out. You guys, that's just 3 times 1 over x. And then when you take the antiderivative, that 3 will come along. And then you'll take the antiderivative of 1 over x, which is natural log, but because I'm introducing the natural log into the problem, I can't assume anything about x, so I just put it in absolute values to be safe, and then I add my plus c. What about this one, you guys? What if I have y equals 5 over x cubed? And I want to take the antiderivative. We need to know when it's natural log and when it's not. You guys, this is 5 over x cubed. Do I need a natural log on this problem? I mean, the x is on the bottom, just like it was over here, and I had to use a natural log. Why is this not a natural log problem? Well, it's because I can rewrite this as 5x to the negative 3, and the power rule works on negative 3. The only one it doesn't work on is negative 1. So you guys, you're going to have to make decisions. Over here where I had 3 over x, that's 3 over x to the first. If you rewrote this, it would be 3x to the negative 1, and you would see that the power rule breaks down. But it only breaks down for negative 1. Any other power on x is going to be fine. So you just have to know when to use the natural log and when not to. So 5x to the negative 3, I can handle this. I'm going to bring the 5 along. My n is negative 3, so I'm going to have 1 over n plus 1. So 1 over negative 2, x to the negative 2, and then I have my plus c. So you could end up just writing this as, looks like -5/2 x to the -2 would be a nice version of it. Let's look at the next one I have on the list. What if I start with e to the x? You guys, this should be the easiest one because let's recall the derivative. If I started with e to the x and I took the derivative, what did I get? The exact same thing, e to the x. So if that's the case, then how do you think it looks going backwards? You guys, if you started with this and you ended with the same thing, I think it's going to look exactly the same going backwards. You want the antiderivative of e to the x? Well, it's going to be e to the x plus c, of course. So it stays the same always. What if I've got a coefficient on it? What if I have y equals 3 e to the x? Well, I think I'm going to handle it like I handle coefficients in general. You guys, I'm going to have the antiderivative of 3 e to the x dx. And that's going to equal, remember the 3 is a coefficient, so it just comes along. I take the antiderivative of e to the x and I get e to the x again. So it's still just the same. I'm just bringing the coefficient along here. Now, e to the x is very nice, but sometimes it does change, right? Sometimes I do have to do more than just copying down the same thing. So let's think about what that kind of case would be. You guys, what if I have e to the 5x as my original function? And I want to find out what the antiderivative is. You guys, this is what I'm going to do. So I want to take the antiderivative of e to the 5x dx. I have to think about, well, is it just going to be e to the 5x again? I mean, do I have to worry about that 5? You guys, let's recall, and it'll be really easy to see what we're going to do. So when I recall today, this is derivative talk, right? So if I started with e to the 5x and I took the derivative of that, what would I do? You guys, doesn't that 5 end up being multiplied? And I get 5e to the 5x. Remember, the reasoning behind that is the chain rule. We bring the e to the 5x down the exact same, and then we have to multiply by the derivative of 5x. But you guys, what we end up with is 5e to the 5x. So what happened to this 5 was that we ended up putting it in front with multiplication when I took the derivative. What do you think is going to happen with that 5 when I go the other direction? You guys, it's going to end up being in, this 5 is going to go in the front just like this one did, but it's not going to be with multiplication. It's going to be with division. You guys, I'm going to get 1 over 5 e to the 5x plus c, of course. And you might wonder, okay, so why is that? I have the 5 and then I bring it in front as 1 over 5. You guys, go backwards. You guys remember how to check your answers. Take the derivative of this and see what happens. You guys, you're going to get this, right? Because that 5 would end up coming down in front and canceling out the 1/5. And you'd be back to e to the 5x. So you guys, if you've got a number with your x up here, so let's do another one just like it. You guys, if I've got y equals e to the -4x, how am I going to take the antiderivative of that? Well, I'm going to bring that -4 in the front with division. I'm going to end up with -1/4 e to the -4x plus c. So just like before, the actual e term always does come down as is, like it did with the derivative. It's what's happening around it that changes a little bit. So we just have to be careful, you guys. Anything that you would have done to take the derivative, we have to do that in reverse. Let's see. So you guys, let's just put some, I'm just going to give you a couple of functions where we put this all together. You guys, so in this next example, I want to take the antiderivative of the following. You guys, I have x cubed plus 4x to the negative 2 minus the square root of x plus 3. Yeah, dx. All right, guys. So just like with derivatives, you've got multiple terms. You can take the antiderivative of each term separately. You guys, this is the first time we've had more than one term, but that works exactly the same way. So you guys, you can just take them all separately. So let's see what happens. Let's start with the x cubed. Remember, in this case, n would be 3. What's your power rule look like? I'm going to turn it into 1, hold on. 1 over n plus 1 x to the n plus 1. That's your power rule. So if n is 3, then n plus 1 is 4. So I need 1 over 4 x to the 4th. Now I'm done with that term. Plus, you guys, this time n is negative 2. What's negative 2 plus 1? Well, that's negative 1. So you guys, this 4 is a coefficient. It just comes down. Then I do the power rule. So I'm going to use 1 over negative 1 x to the negative 1. And I'll simplify that on the next step. You guys, what about this minus square root of x? Well, let's rewrite it. Just rewriting it the same. Okay, let's actually rewrite it as something different. Let's write it as x to the 1/2, and we found this one before. So let's see, I had x to the 1/2. It is a minus, so go ahead and put that there. If this is n, remember we found n plus 1 was 3/2. So it's going to be 1 over 3/2 x to the 3/2. And again, we'll simplify that in a minute. What about this plus 3? You guys, really, really, really be careful with your constants, because when you see a plus 3, I know in your head you want to get rid of it because you think it goes away because your head is thinking in derivatives. Constants do not go away when you're going backwards. You guys, if your derivative is 3, what did that come from? It had to have come from 3x. You guys, if you start with 3x and you take the derivative, what do you get? You get 3. So if I start with 3, I'm going to put an x on it. Anytime you have a constant, all you have to do is put an x on it. Now, this isn't a special rule. It's actually still the power rule. But it's just easier if we don't have to think about it that way. You guys, the easiest thing is just to say, if you have a constant, just stick an x on it, because that's where it came from. Okay, so I have all of this, and then at the end, I'll definitely have a plus c, so I might as well start writing it in now. And the only thing I can do from here is just simplify. You guys, I got 1/4 x to the 4th plus, or let's say this is just negative 1, right? So let's say this is minus 4 x to the negative 1. Remember what 1 over 3/2 is. It's really 2/3 x to the 3/2 plus 3x plus c, and that's it. So I just went term by term. So I know this is a lot to take in, definitely, guys. We're going to be in chapter 13 for a few sections, so you can go ahead and try to start getting into the integration habit. Not that I ever want you to break your derivative habits. Obviously, you're going to have to take derivatives again at some point. You just have to be able to, let's say we have to compartmentalize, you guys. Right now, we need to put the derivatives away, and we need to use the integration or the antiderivatives. We're going to do one more, and then I'll be done with you for the day. Let's do one with e's and natural logs, you guys. So I'm going to have Antiderivative of 3e to the 4x minus 2 over x. Now, I want you to notice something I'm doing in the notation. When I have more than one term that I want to take the antiderivative of, notice that I am using parentheses, and we do have to use parentheses. And the dx goes on the outside of them. I want you to think about making sure your dx applies to both terms. We're taking both of these terms with respect to x. But whatever makes you remember, you definitely need parentheses because you're not saying the same thing if you're not having them. Okay, so let's work. All right, so this 3 comes down because it's just a coefficient, right? What do I do with the e to the 4x? Well, remember, I'm going to take this 4, where it would usually just come down with multiplication, taking the derivative. I'm going to bring it down with division. So you guys, anytime I have a number here with the x, it's coming down with division. But you're not adding or subtracting to it. You guys, it just comes down as is. So I'm going to have the 1/4 and then e to the 4x, just the same. Now, the minus 2 over x. Remember, you can take this minus 2 out. You could say this is minus 2 times 1 over x. You can make that change. So you can just have the minus 2 here. And then what's the antiderivative of 1 over x? Remember, that's natural log x, but every time you're the one who introduces a natural log into the problem, you have to have absolute values. And then we're going to have a plus c. Honestly, on this one, the only thing that you might simplify, you could always call this 3/4 e to the 4x. Then I have minus 2 natural log absolute value x plus c. You'll notice there's homework open. It's just practice. It looks a lot like these do, to be honest with you. You're just going to be doing examples just like we've done. I would encourage you to look at it. It's not due till Sunday, of course. I would encourage you to look at it before our next class. You know, you want to get good at this as fast as you can so we can continue using it. And obviously there's going to be harder ways we use it. So you want to be good at the basics, basically basics. Oh my gosh, guys. Anyway, I cracked myself up. So anyway, look at the homework if you can, and if you have time, on Friday. So guys, I have a meeting up in Edmond. And so I was thinking about just being on campus on Friday, for class too. There's no reason not to. So if you do want to come, in person, if you're an in-person student and you want to come in person on Friday, I will be there in our classroom. I know it's been a while, but it's 109. And we can do that. Let's see. What else was I going to say?
Yeah, I'd be done for that.
Okay. Yeah. So yeah, I'll be there. You know, and if you really do like Zooming, that's fine. You know, there's good things about it, but just since I'll be there, if you want to be there, then come. And I'll send an email about it too for people who aren't here right now. So anybody who wants to come in can come in. But I think that's all I have for you here. So I would encourage you to look at the homework before Friday. I will also be in class on Friday if you're an in-person student. And that's your decision to make. You don't obviously have to come to class. And I think that's it, guys. So I think I will just possibly see you on Friday, either Zoom or in person.